One of The next section is the first of two sections discussing potassium balance. The maintenance of potassium balance is essential for the normal function of excitable tissues, such as the nerve, skeletal muscle, and cardiac muscle. Recall from chapters 1 and 4 that the potassium concentration gradient across excitable cell membranes sets the resting membrane potential. Recall also that changes in resting membrane potential alter excitability by opening or closing gates on the sodium channels. These are responsible for the upstroke of the action potential. Thus, changes in either intracellular or extracellular potassium concentration alter the resting membrane potential and, as a consequence, alter the excitability of these tissues. Most of the total body potassium is located in the intracellular fluid space. 98% of the total potassium content is in the intracellular compartment and 2% is in the extracellular compartment. A consequence of this distribution is that the intracellular potassium concentration is much higher than the extracellular concentration. The intracellular potassium concentration is approximately 150 milliequivalents per liter, whereas the extracellular concentration in the normal range is approximately 4.5 milliequivalents per liter. You can notice also that the intracellular potassium concentration is very similar to the extracellular sodium concentration. Conversely, the intracellular sodium concentration is very similar to the extracellular potassium concentration. This balance is ultimately maintained by the activity of the sodium-potassium ATPase. Recall that the sodium-potassium ATPase is present in all cell membranes. One challenge to maintaining the low extracellular potassium concentration is the large amount of potassium present in the intracellular compartment. A small shift of potassium into or out of the cells can produce a large change in the extracellular potassium concentration. The distribution of potassium across cell membranes is called internal potassium balance. Hormones, drugs, and various pathologic states alter this distribution and, as a consequence, can alter the extracellular potassium concentration. Another challenge in maintaining the low extracellular potassium concentration is the variation in dietary potassium intake in humans. Dietary potassium intake can vary from as low as 50 milliequivalents per day to as high as 150 milliequivalents per day. To maintain potassium balance, urinary excretion of potassium must be equal to potassium intake. Thus, on a daily basis, urinary excretion of potassium must be capable of varying from 50 to 150 milliequivalents per day. The renal mechanisms that allow for this variability are called external potassium balance. Table 6-8 on page 277 of the text outlines internal potassium balance, with shifts across cell membranes being the primary means of maintaining potassium balance. The table outlines causes of potassium shift out of the cells, resulting in hyperkalemia, as well as causes of potassium shift into the cells, leading to hypokalemia. Recall that internal potassium balance is the distribution of potassium across cell membranes. To reemphasize, most potassium is present inside the cells, and even small potassium shifts across cell membranes can cause large changes in potassium concentrations in the ECF and blood. The effects of hormones, drugs, and pathologic states that alter this distribution of potassium are summarized in Figure 6-29 in Table 6-8. A shift of potassium out of cells produces an increase in the blood potassium concentration. This is referred to as hyperkalemia. A shift of potassium into cells produces a decrease in the blood potassium concentration. This is called hypokalemia. Insulin is one hormone that stimulates potassium uptake into cells by increasing the activity of the sodium-potassium ATPase. Physiologically, this effect of insulin is responsible for the uptake of dietary potassium into the cells following a meal. Thus, in response to food ingestion, insulin is secreted by the endocrine pancreas. One effect of this insulin, in addition to the stimulation of glucose uptake into cells, is to stimulate potassium uptake into cells. This action ensures that ingested potassium does not remain in the ECF and produce hyperkalemia. Deficiency of insulin, as occurs in type 1 diabetes mellitus, produces the opposite effect. There is decreased uptake of potassium into cells and hyperkalemia. When a person with untreated type 1 diabetes mellitus ingests a meal containing potassium, the potassium remains in the ECF because insulin is not available to promote its uptake into cells. Conversely, high levels of insulin can produce hypokalemia. Further, insulin is often used in the treatment of hyperkalemia to push potassium into the cells. Acid-base abnormalities often are associated with potassium disturbances. One of the mechanisms underlying potassium balance involves hydrogen-potassium exchange across cell membranes. This exchange is useful because the intracellular fluid has considerable buffering capacity for hydrogen. In order to take advantage of these buffers, hydrogen must enter or leave the cells. To preserve electroneutrality, however, hydrogen cannot enter or leave cells by itself. Either it must be accompanied by an anion, or it must be exchanged for another cation. When hydrogen is exchanged for another cation, that cation is potassium. In alkalemia, the hydrogen concentration in the blood is decreased. Hydrogen thus leaves the cells and potassium enters the cells. This will result in hypokalemia. On the other hand, in acidemia, the hydrogen concentration in the blood is increased. Hydrogen enters the cells and potassium leaves the cells. This will result in hyperkalemia. Acid-base disturbances do not always produce a potassium shift across cell membranes. However, it is important to note the following exceptions. First, respiratory acidosis and respiratory alkalosis typically do not cause a potassium shift because these conditions are caused by a primary disturbance in carbon dioxide rather than free hydrogen. Since carbon dioxide is lipid soluble, it freely crosses cell membranes and needs no exchange with potassium to preserve electroneutrality. Second, several forms of metabolic acidosis are caused by an excess of an organic acid. Examples are lactic acid, keto acid, or salicylic acid. This does not require a potassium shift, as electroneutrality is maintained by the associated anion with the hydrogen. When an organic anion such as lactate is available to enter the cell with hydrogen, electroneutrality is preserved, and no shift of potassium is required. Chapter 7 discusses the conditions under which an acid-base disturbance causes a potassium shift and when it does not. Catecholamines alter the distribution of potassium across cell membranes by two separate receptors and mechanisms. Activation of beta-2 adrenergic receptors by beta-2 agonists such as albuterol increase the activity of the sodium-potassium ATPase. This will cause a shift of potassium into the cells and may produce hypokalemia. On the other hand, activation of alpha-adrenergic receptors causes a shift of potassium out of cells and may produce hyperkalemia. The effects of adrenergic agonists and adrenergic antagonists on the blood potassium concentration are thus predictable. Beta-2 adrenergic antagonists, such as propranolol, will cause a shift of potassium out of cells. Alpha-adrenergic antagonists cause a shift of potassium into cells. Hyperosmolarity, or an increase in the osmolarity of the ECF, causes a shift of potassium out of cells. The mechanism involves water flow across cell membranes, which occurs in response to a change in ECF osmolarity. For example, if the osmolarity of ECF is increased, water will flow from the ICF to the ECF because of the osmotic gradient. As water leaves the cells, the intracellular potassium concentration increases. This then will drive diffusion of potassium from the ICF to the ECF. A simpler way of visualizing the mechanism is to think of water flow from the ICF to the ECF as dragging potassium with it. All these previous mechanisms are employed in the treatment of hyperkalemia. When there is hyperkalemia or elevated serum potassium, the clinicians will often treat patients with insulin to drive potassium into cells, bicarbonate to drive potassium into cells, but to give the bicarbonate over a slow period of time to not increase osmolarity, thus preventing potassium from leaving the cells. Cell lysis, or the breakdown of cell membranes, releases a large amount of potassium from the intracellular fluid space and produces hyperkalemia. Examples of cell lysis include burns, rhabdomyolysis, or the breakdown of skeletal muscle, and malignant cells being destroyed during cancer chemotherapy. Exercise can also cause a potassium shift out of cells. The depletion of cellular ATP stores opens potassium channels in the muscle cell membranes, and potassium moves out of the cells down its electrochemical gradient. Usually the shift is small and produces only a slight increase in blood potassium concentration, which reverses during a subsequent period of rest. However, in a person treated with a beta-2 adrenergic antagonist, which independently produces a potassium shift out of cells, or in those with impaired renal function in which potassium cannot be adequately excreted, strenuous exercise can result in hyperkalemia. As an aside, potassium shift out of cells assists in the local control of blood flow to exercising skeletal muscle. Recall that blood flow in exercising muscle is controlled by vasodilator metabolites, one of which is potassium. As potassium is released from the cells during exercise, it acts directly on skeletal muscle arterioles, dilating them and increasing local